Okay. All right, let's get going. So where we are in the scheme of things is filter design. In particular, we're talking about IIR filter design using transformation technique. So let's write that down. IIR filter design using transformation. And we already talked about impulse invariance. And then we also talked about bilinear transformation. And last time what we talked about is using bilinear transformation to design low-pass filters. Okay. And today what we're going to talk about is to design high-pass filters. Okay. In particular, we're going to talk about two methods of designing high-pass filters using bilinear transformation. One of them is to transform a low-pass analog filter to design a high-pass digital filter. So in this scheme we use low-pass analog filters. What I mean we transform a low-pass analog filter to design this high-pass digital filter that we're after. Remember, all of these things are digital filters, right? Here, when the low-pass filter design technique, we used we transformed low-pass analog filters to design low-pass digital filters. So here, we can either use low-pass analog filters directly to design high-pass digital filters, or we can use high-pass analog filters. So I'll explain these two. So this is what we're going to be talking today, and this and that. I'll explain all of these blobs in just a little bit. Okay, just so that you know where we are in this kind of a tree. Okay. Okay, so I call this scheme 1 and I call this scheme 2. So let me get going with scheme 1. So I call this approach 1 to design digital high-pass IIR filters. Okay, so approach 1 basically consists of the following. You start with a continuous time or analog low-pass filter, which I call H sub A of S1, and then you do a continuous to continuous transformation, and you end up with a continuous time high-pass filter, which I call H sub A prime of S2. And then you do a continuous to discrete time bilinear transformation. And then that results into h sub d of z, which is your discrete time filter. This is a discrete time filter, which is also a high-pass filter. There's a lot of acronyms here. C stands for continuous. Little a and a prime stand for analog. And little d stands for discrete, and also big D. And T just stands for time, so just so that you can understand. And then H stands for high. HPF is high pass filter. And LPF means a low pass filter. Just so that you can get all the acronyms right. Okay. Okay, so sort of just to repeat this thing one more time, I start with a continuous time low pass. I end up with and then I transform it into continuous time high pass filter, and then I transform this continuous time high pass filter to discrete time high pass filter. So, really, pictorially, what's happening, at least in this step. Could you zoom up just a tiny bit? Okay, so at least in this step, what's happening is this. I have, as a function of omega 1, I have a low-pass filter that sort of looks like this, and it has a transfer function, h sub a of s1, and I'm going to transform that using this continuous to continuous conversion into a high-pass filter. As a function of omega 2, that sort of looks like this. And that gets transformed into h sub a prime of S2. So this is a low-pass filter in the sense of being a high-pass filter. Okay. So there's essentially two transformations. One is continuous to continuous, which is what I've drawn here, and then a continuous to discrete, which I'll talk about in just a second. So what would be a good proposal for doing this C to C transformation? In other words, what's a good thing? And I would propose the following. H sub a, I would say h sub a prime of S2. Essentially what you have to do is invert wherever omega 1 is small, you want to make omega 2 be large. Whenever omega 1 is large, you want omega 1 to be small, right? Because you're converting a low pass filter to a high pass filter, these are sort of opposites of each other. If h of omega, if this low pass filter at large values of omega 1 attenuates for a low pass filter, as a high pass filter you want it to attenuate for low values of omega, and vice versa, because a high pass is just the opposite of a low pass, right? There has to be this inversion type thing that goes on, right? And so a reasonable proposal is to say is something of this nature. H sub a of S1, replace S1 with some constant, let's say omega sub u over S2. So S1 and S2 are inversely proportional to each other. This is just some constant. So that inversion that I was talking about is sort of depicted by this relationship. And so that's just my proposal. Let's just see if it is any good. And where this omega sub u is just some positive constant, as always. We have these constant factors. So the first question that comes to your mind is, would this transformation have the usual properties that we want? Does the j omega 1 axis in this S plane here get transformed into the j omega 2 axis in this S2 plane? So here's the S1 plane, here's the S2 plane. Does those relationship hold? So let's plot that. This is the S1 plane, and this is the S2 plane. And S1 plane has sigma 1 plus j omega 1, and S2 has sigma 2 plus j omega 2. And the question I'm asking is, does this axis here get mapped into this axis using this proposed transformation? So let's show that the j omega 1 axis is transformed into the j omega 2 axis. How do we do that? Well, you just let S1 be equal to j omega 1. Substitute that into the transformation and see what value of S2 you get. Okay, so this is equal to, the transformation is omega u sub u over S2. That means that S2 is equal to omega u over j omega 1, which is the same as minus j omega u over omega 1, which, but S2 is just nothing but sigma 2 plus j omega 2. So equating the real part of this to the real part of that, and the imaginary part of this to the imaginary part of that, from here, what we conclude is that sigma 2 is equal to 0, and we want the imaginary part to be the same. That means sigma omega 2 is equal to minus omega sub u over omega 1. So this is the image, or the mirror, or the mapping of the j omega 1 axis in the j omega 2 plane. So what did it get mapped to? It got mapped into the line where sigma 2 is equal to 0. Well, sigma 2 equals 0 is this axis. So exactly, so this axis, this j omega 1 axis, did indeed get mapped into the j omega 2 axis. And if I give you a value of omega 1 like 5, then let's say omega 1 is equal to 5 here, it corresponds to minus omega u over 5. So it'll map somewhere here. Okay, so for every value here, it gets mapped somewhere. For every point in here, I can find a mapping of it on this other axis. So this is the mirror. So indeed, it is true. So yes, j omega 1 does get mapped into j omega 2. Thank God. So now the other thing we want to make sure is that the left half plane, it also maps to the left half plane. And the reason was we wanted to make sure that causal and stable filters in one domain get mapped into causal and stable filters in the other domain. So the question, so we want to show that the left half plane maps in S1, I mean, maps onto the left half plane in S2, and that's question mark. And it's pretty straightforward to show. How would we go about doing that? You just pick a random point somewhere here and show that indeed it gets mapped into the left half plane. So let's say I pick a point here where sigma 1 is equal to, I don't know, minus 5 or something like that. Then you plug it into this relationship, and I'm sorry, you plug it into this relationship, S1 is equal to omega u over S2, then you find out that that gets indeed mapped into somewhere on the left half plane, just by virtue of an example. So just because the mappings are continuous, and as long as you prove one point on the left half plane here gets mapped into one point, then you can pretty much conclude that the entire left half plane gets mapped into the entire left half plane there. So the answer is yes, and therefore from here we can conclude that causal plus stable gets mapped in S1, gets mapped into causal and stable in S2. Okay? Yeah, question.
Suppose we have something like an integrator, which is just 1 over s, and you that is, well, marginally stable in some sense. But if I transform it, it becomes a differentiator, which is not.
That's also marginally stable.
Is it realizable?
What do you mean? Why would it not be realizable?
Because it needs a future value and a past value if you want to interpolate, right? The differentiator will need a future value and a past value for the slope.
Well, it depends. So let's be more specific. So you're saying h sub a of S1 is 1 over S1. Then you go into this thing, into this relationship here, and replace S1 with omega over S2. And so what you get is S2 over omega sub u. So that is your differentiator, right? So what's the question? It's still a rational transfer function, right?
But you usually say that a differentiator is not realizable because a differentiator is, if you want to find the derivative at that point, you need a future value and a past value so that you can kind of interpolate and find the slope instantly at that point.
You're saying it's not implementable because it's not causal anymore? But yeah, I mean, strictly speaking, an integrator is part of the reason that perhaps you're getting into trouble is the integrator has a pole on the j omega axis. So that automatically doesn't strictly make it a causal, that strictly doesn't make it a stable system. Does it? So when you come back to, when you transform it, it's certainly a rational transfer function. So that's not really a big issue. But the question is it causal and stable? It doesn't really have a, well, to begin with, you didn't start with a stable system. So whether or not it gets transformed into a stable system, I mean, that's already, having that as a system is already a bit of an issue already because it's not really stable, right? But the causality aspect of it, yeah, I mean, the transfer function, if you will, for a differentiator is just a j omega, right? It's a straight line as a function of omega. You could design a differentiating kind of thing by introducing, in discrete time domain anyway, introducing a little bit of a delay and get rid of the causality problem, right? You're still taking the derivative, but not derivative at that instance. But let's discuss that offline a little bit more. Yeah, question.
In continuous time, does the high-pass filter extend to infinity?
Mm-hmm.
The energy, it's not stable, right?
Well, it depends what you mean by does it go into infinity? Are you saying that does this thing go on forever? There are high-pass filters that are stable. You can, well, I'm just drawing this as a hand-drawn characterization of a high-pass filter, right?
Decay at some point.
In other words, it has to be bandpass filter for it to be stable. That's what you're saying. Let's see. Let's nail down the definition of stability. As you know, there's lots of different definitions of stability. So what we're concerned about is Bibo stability. So if you have Bibo stability, it means your impulse response is absolutely summable. Does that necessarily mean that something like this is disallowed? I'm not exactly sure. Are those two mathematical statements equivalent? Well, having your impulse response being absolutely summable, does that necessarily preclude having what you're defining as stability is now that the integral of magnitude square of this is what? Finite.
So that means
are those things the same necessarily?
It has to be square summable.
Exactly. Exactly, because the area underneath squared integrated over is equivalent to having the
right.
impulse, yeah, using Parseval's theorem, right? Right. So the answer is, yeah, if this thing goes on forever and it's not square summable, right, then the impulse response for it is probably also not square summable. But does that mean anything about Bibo stability, or is there a tight relationship between square summability type of stability? Having h of t squared dt integral from minus infinity to infinity, having that being finite, is that the same as having h of t being finite?
I thought that absolute summability is a stronger requirement than square summability. So if you're not square summable, then you're not absolutely summable. I don't know. Is that right?
Not necessarily. What is true is that we could say it's something like summations of over n or 1 over n diverges, but summation of 1 over n squared converges. That you could say. Whether or not absolute In other words, is it true if you have h of t absolutely summable, does the absolutely or integrable, it doesn't matter. Is that a stronger or a weaker requirement than having a square? I'm not sure one can imply one versus the other. Again, let's pick that up offline. So I do want to continue with this discussion here. So, so pretty much a point on the left half plane maps into a point in the left half plane. So if you had started with a causal stable filter, you end up with a causal stable high pass filter. And so what can we say? So essentially what we can say is that the left half plane in S1 gets mapped into a left half plane in S2. So how do we translate that? So how can we, now that we have this relationship, how can we do the translation of the specs? So translate the specs, and what we get is h sub a prime of omega 2. Now that we have this relationship, we can write down in terms of h sub a of omega 1. Well, how is that relationship? Well, you have to replace omega 2 with this relationship. Or in other words, omega 1, the opposite of this relationship, minus omega sub u over omega 2. Okay? But to get rid of this negative sign, I'm just going to play a little bit of a trick. So I'm going to assume that h sub a of t is real. That means the frequency response of h sub a is magnitude of the frequency response is symmetric. What that means is that h sub a of omega 1 is equal to h sub a of minus omega 1. And so combining these two things together, I can just say that h sub a prime of omega 2, magnitude here, is equal to magnitude of h sub a of minus omega 1 I'm going to replace h sub a of omega 1 with h sub a of minus omega 1 because they're equal to each other. Evaluated at omega 1 equals minus omega u over omega 2. And then from here I can conclude that h sub a prime of omega 2 magnitude is equal to, now I'm going to replace minus omega 1. I'm going to make this omega 1, h sub a of omega 1, evaluated at omega 1, and now this minus sign cancels this other one. I get omega sub u over omega sub 2. Okay? It's just algebraic manipulations. If h sub a is real, then this relationship holds true, and I can essentially get rid of this negative sign here. That's all I'm trying to say. So what, pictorially, what kind of a picture do we have here? Let's plot that. So we have the omega 1, omega 2 transformation that looks something like this. This curve here is omega 2 is equal to omega sub u over omega sub 1. And if we're given a low-pass filter, for example, h sub a of omega 1 with this kind of a spec as a function of omega 1 with this kind of a spec, it's supposed to be 1 here, 1 minus delta 1 here. It's omega p1 here and omega s1, and it has a ripple of delta 2. Then we can translate this set of specs into a high pass spec, or vice versa. If you have a high pass spec, you can translate that into a low pass spec. But let's just go over that. So the high pass filter here is a function of omega 2, and what we get is h sub a prime of omega 2 magnitude. So what we have to do is transform omega p1. So make that come all the way up here. That's omega p1. Go all the way there, and that gives you omega p2, and go all the way up here. That's omega p2. And then you map also omega s1. Go all the way here. That's omega s1. You hit the curve. You find the other value of it, omega s2. This is the curve that transforms omega 1 to omega 2. It transforms omega s1 into omega s2. And here omega s2 is the new frequency that corresponds to this. And so from omega s2 and larger values of omega, we want the filter to take on the magnitude within delta 2. So omega s1 and larger values of omega s1 correspond to smaller values of omega 2. So this frequency range corresponds to this frequency range here. This frequency range corresponds to this frequency range here. So in this range, we have to have spec of no more than delta 2. So the filter magnitude is within delta 2. And this frequency range corresponds to this point, corresponds to that point, and these points correspond to these points. So this frequency range corresponds to this frequency range. And here, they're supposed to have 1 minus delta 1. You have 1 minus delta 1. So here's the spec translation from a low-pass filter to a high-pass filter using this transformation. Question?
Can you clarify what omega sub u is? Is it?
It's a constant.
So it should be a linear. Omega 1 and omega 2 should be a linear. That should be that plot on the upper right. Should
No,
be linear.
it's one of them is one over the other. Yeah.
Right, okay.
Times a constant. It's just a constant.
Okay, thank you.
Yeah. Actually, you're right. It's a bad notation that I'm choosing. Maybe I should just use a K. Just get it done and over with. Because there's so many omegas hanging around. That's one more omega makes the whole thing much more confusing. Just think of it as K. Okay? So is that clear? So this is the same way as we're doing analog to digital transformations. Now we're doing analog to analog transformations. Okay. So that's really all I want to say about this method. So let's just for clarity purposes outline all the steps of one uses in designing a discrete time or a digital high-pass filter using this technique. So what would be all the steps? Let's come back here. So steps to design an IIR digital filter using using this technique that we just talked about. We call it approach 1. So as usual, we start with some sort of a spec in the discrete time domain for the high-pass filter. Okay? Discrete time domain for the high-pass filter. That's given to us by the system designers, and we don't have much control over it. You're stuck with it. So the first thing that you do, you translate the specs from a discrete time high-pass filter into a continuous time high-pass filter. So translate the specs. Let me just, before I get into these things, let me just okay. Yeah. So you yeah. So just hold on this for just a second. So coming back here, what we've outlined here is a way of designing a continuous time high-pass filter from a continuous time low-pass filter, right? But this is part of a bigger scheme that we talked about here, right? So coming back one step higher, I've spent the last 10 minutes or so talking about this continuous to continuous design, and I've told you I've talked about the transformation that takes you from here to here, okay? In essence, that's not all the transformations we need. We need another one to take us from this high-pass filter in continuous time to a high-pass filter in discrete time. Okay, so we have now sort of two sets of transformations, if you will. So that's why the final design is a little bit more complicated than what we had before. So you start with the specs. You translate the specs from a discrete time high-pass filter into a continuous time high-pass filter. And how do you do that? That's the reverse of this step, right? This is the reverse of whatever bilinear transformation you're using to go from a continuous time high pass filter to a continuous time low pass filter, which could be the same one as we talked about last time. Okay, nothing fancy, nothing different, etc. But you pick your bilinear transformation and do the reverse of this specs. So now you have a set of specs in continuous time high pass filter. Okay, so then the next step is translate the specs one more time. So you translate the specs of a continuous time high-pass filter into what now? A continuous time low-pass filter, right? Which is this step we just talked about. Into a continuous time low-pass filter. And now go ahead and design the continuous time low-pass filter, and you can use any of these favorite techniques, Butterworth or Chebyshev or elliptic or anything you like. And now you have to undo all the steps that you did here. Okay, so now you have a continuous time low-pass filter. You have to first, using this thing, go back to get your continuous time high-pass filter. So using a dual to step 3, what you want to do is you want to transform your continuous time low-pass filter into a continuous time high-pass filter. And now you have a continuous time high-pass filter, which is what you got here. And now you have to undo step 2 here, which is transform whatever you did in this step to translate the specs. You want to transform the continuous time high-pass filter into a discrete time now high-pass filter. And that's the end of it. Is everybody with me? So it's just more of the same thing. I don't know how to solve a problem. I just reduce it to something I know how to do. This is the one thing I know how to do. That the art of designing continuous time low-pass filters, Butterworth, elliptic, Chebyshev, is just well understood. So our goal is to translate it, get ourselves to this point. And we get ourselves to that point, instead of using one transformation, it's using two transformations. One of them is just discrete to discrete. It's just get me from go from a discrete time high-pass filter to a continuous time high-pass filter. And for that, you can use the same bilinear transformation we talked about last time. Not a big deal. And for the second step, then you can do what we just talked about, the continuous time to continuous time sort of translation, and do this. Okay? Okay, any questions on this? So I'm going to change gears just a little bit and talk about the second approach for doing this problem. And the second approach also is a two-step transformation technique, but the two steps are slightly different. So, so I call it approach number 2 to designing high-pass filter, discrete time, IIR, high-pass filter using transformation. And here, the block diagram looks a little bit different from what we had before. In this first scheme, we designed our ultimate discrete time high-pass filter by first transforming it into continuous time high-pass and then a continuous time low-pass. Here, what I'm going to do is slightly different. I'm going to still start with a continuous time low-pass filter because I know how to design those. And I do a continuous to discrete time transformation to get a discrete time low-pass filter. And then I do a discrete to discrete transformation, which I'll talk about now, in order to get the discrete time high-pass filter. Okay? So in some sense, I reduced the problem to the problem that we discussed in the last lecture, which was how to design discrete time low-pass filter. Well, how to design discrete time low-pass filter was based on how to do continuous time low-pass filters. Right? So the proposal that we have is as follows. So I'm going to name these things. I call these h of z1. Okay. And I'm going to call this, let's see, I'm going to call this h sub, and I'm going to call this h sub, I don't know, z2, but I have to name this a different name. So why don't I refer to this thing as h sub d or something like that? So going from discrete time low-pass filter to continuous time low-pass filter, that's something we talked about already in the last lecture using the bilinear transformation that I put up, and that's pretty well understood. The part that's not well understood is this part. What transformation can I come up here? And what I propose, once again, is this. H sub d of z2 is h of z1 with z1 replaced by the following expression. It's minus alpha plus z2 over 1 plus alpha z2, where alpha, again, is some real number that's a parameter and you can set it to any values, and its choice becomes clear in just a second. But magnitude of alpha has to be smaller than 1. So that's what I'm proposing for this part, for this discrete to discrete transformation. So the usual set of questions come up. Does it map? So this is now a discrete to discrete trans. Can you zoom up, please? Go up, please. Does this map the unit circle in the Z1 domain to the unit circle in the Z2 domain? So does it map e to the j omega 1 onto e to the j omega 2 in the Z2 plane? This is in Z1 and this is in Z2. It's pretty straightforward to show that indeed it does. So you just let Z1 to be equal to, let Z2 be equal to e to the j omega 2. What I get then is Z1 is equal to minus alpha plus e to the j omega 2 over 1 plus alpha e to the j omega 2, which is the same as minus. I'm going to take a factor out here, e to the j omega 2, 1 plus alpha e to the minus j omega 2, and then 1 plus alpha e to the j omega 2. Okay. Now I'm going to take the magnitude of Z1. Okay. What can I say about the magnitude of Z1? It's equal to magnitude of minus 1 times magnitude of e to the j omega 2 times magnitude of this remaining thing, which is magnitude of 1 plus alpha e to the minus j omega 2 over magnitude of 1 plus alpha e to the j omega 2. And what can I conclude about magnitude of Z1? It's just 1, because these two are complex conjugates. And that's exactly the reason I factored out e to the j omega 2 out, so that I make this complex conjugate of the other one. So magnitude of Z1 is 1, so that means that if I let Z2 be in the unit circle, it gets mapped into Z1 where the magnitude is 1, so that is the unit circle as well. That's the unit circle in Z1. So that means yes, e to the j omega 2 did get mapped into e to the j omega 1. That means that pictorially, what that means is that if I were to, this is the Z1 plane, or the Z2 plane, and this is the Z1 plane. So e to the j omega 2 here, this is e to the j omega 1. So this thing does get mapped into this thing. Okay, and you can also show, I'm not going to do it, but the question is, does the inside of this get mapped to the inside of this one, or does the inside of this get mapped to the outside of this? And the answer is that the inside of this, you just pick a random point here, and you can show that it gets mapped inside. So you can show that the inside of the unit circle gets mapped into the inside of the units in Z1, or in Z2 gets mapped into inside of the unit circle in Z1. So that's easy to show, and that shows that the causal plus stable high-pass filters in one domain gets mapped into a causal unstable low-pass filter in the other domain. And the precise mapping then is what? Coming back up here, the precise mapping is nothing but this. Because we showed magnitude of Z1 here is equal to 1, the precise mapping is e to the j omega 1 is equal to minus alpha plus e to the j omega 2 over 1 plus alpha e to the j omega 2. So that's the precise mapping between omega 1, little omega 1, and little omega 2. All I do is replace this Z1 with e to the j omega 1. Why? Because I showed the magnitude of this thing is just 1. Okay, so having this relationship now, this is our mapping. I can sort of write, can you zoom down so I can write down here? So I can sort of say that omega 1 is equal to some function of omega 2 and alpha. From here to here, this function is just complicated relationship. Okay? So let's just, I want to show, for reasons that becomes clear in just a second, I want to show that I want to get rid of a negative sign. It always takes a lot of derivation to do it, and it buys you very little. But it's good to just show this thing that I'm talking about. It'll become clear in 1 second. I want to show that if omega 1 is equal to f of omega 2 comma alpha, then omega 1 is also the same function of minus omega 2 comma alpha. And I'll show you why I'm insisting on showing that. It becomes clear in a minute. Okay, so what can we say about the mapping between omega 1 and omega 2? Well, we already know that h sub d of omega 2, our filter in the Z2 domain, is just equal to h of omega 1 with omega 1 replaced with this f of omega 2 comma alpha. And it's the same argument as I used 5 minutes ago. If I assume that this filter here has a real impulse response, then its magnitude is magnitude of its frequency response is symmetric. So I can easily show that these two things are more or less the same thing. So assume that h sub d has a real impulse response. And what does then that conclude? Well, that concludes that magnitude of h sub d of omega 2 is equal to magnitude of h sub d of minus omega 2. Because that means the Fourier transform is conjugate symmetric. If the Fourier transform is conjugate symmetric, its magnitude is symmetric, its phase is antisymmetric, right? So here is the magnitude that's symmetric, because I assume this guy has a real impulse response. And then what can I say here? Combining these two things together, what can I say? I can say, well, h sub d of minus omega 2 magnitude is equal to magnitude of h sub d of omega 2 is equal to, and now I'm going to replace this this guy I'm going to replace this guy, h of omega 1 magnitude again, with omega 1 equals to f of not only omega 2 comma alpha, but minus omega 2 comma alpha as well. Because these two things are the same thing. So I can just go back here and replace the omega 2 with minus omega 2. So keep that in mind. We'll just use it in a second. So come back now, and this is our mapping that we were interested in. This is the mapping that now I want to manipulate that and see how does little omega 1 really relate to little omega 2? What is the relationship? So from here, if I can do it for specific values of alpha in order for you to see what's going on. Suppose alpha is equal to 0. That simplifies things tremendously. Then I get e to the j omega 1 is equal to minus alpha plus e to the j omega 2, 1 plus alpha e to the j omega 2. I let alpha equal 0 to that. I get e to the j omega 1 is equal to what? Minus e to the j omega 2. That means that, which is the same thing as e to the j pi times e to the j omega 2, because minus 1 is just e to the j pi, which means that omega 2 plus pi is equal to omega 1. Okay? But now I'm going to use my trick that, so this is my f of omega 2 comma alpha, right? And now that means f of minus omega 2 comma alpha is minus omega 2 plus pi equals omega 1, which means omega 1 plus omega 2 is equal to pi. And why am I insisting on having f of minus omega 2 comma alpha? Well, because now this thing has a much nicer form. It has omega 1 plus omega 2 equals pi. And I already showed 5 minutes ago or 1 minute ago that if I'm dealing with magnitudes, I can just as easily use f of minus omega 2 alpha. And now I showed you that f of minus omega 2 alpha is this nice, good relationship. So bingo, we're done. So this relationship here allows me, which is omega 1 equals f of minus omega 2 alpha, which is the same as omega 1 plus omega 2 alpha, at least equals pi, at least alpha equals 0. I have a simple relationship relating my little omega 1 to little omega 2, right? I see actually a lot of puzzled faces. Yeah, question.
So does this flip the magnitude around or something? Is that why? Is that what it says? It adds up to pi?
Yeah. So that means I'll draw some more pictures in just a second, but that's all that means. If I were to apply omega 1 and omega 2, for alpha equals 0, I get this. I guess this plot. That's right. But I hope you didn't get too confused with these minus omega 2 games that I'm playing with you. Is everybody clear? It's purely algebraic. It's purely algebraic, and the only reason I do it is to get a simple relationship like that. It doesn't have any other significance. Yeah.
When alpha is not 0, can we still have that kind of simple expression?
Yeah, you can. I just did that for alpha equals 0 just to show why I did this minus omega 2 games. I'm just assuming that all the filters we're designing have real impulse response and have therefore symmetric magnitude in their frequency response, and therefore there is substitution. Okay, so now how do these specs get sort of translated? Let's plot that. This is our fundamental relationship, so let's start with plotting that in a nicer way. So this is omega 1, this is omega 2, and this is pi. Omega 1 plus omega 2 equals pi. So this is alpha equals 0, or omega 1 plus omega 2 equals pi. And it turns out that if alpha is not equal to 0, you get curves like this. So this is alpha equals 1, alpha equals 1/2. This is alpha equals minus 1/2, alpha equals minus 1. Okay? So, and then if I were to plot here the omega 1 sort of specs, h of omega 1, this is our low-pass filter, or rather, we want to translate the specs of our high-pass filter to low-pass filter, right? We want to design a high-pass filter. We're given specs for a high-pass filter, and we want to translate the specs of that high-pass discrete time filter to low-pass discrete time filter. This is our picture. Where is it? This is our new picture, right? Ultimately, our goal is to design a discrete time high-pass. And so we're given specs for that, so we want to translate those specs to a discrete time low-pass filter. Okay. So here's our discrete time high-pass, h sub d of omega 2, and we deal with magnitude so that we can play that negative trick there. And this is omega 2, and it's a high-pass filter that we're given. So this is some sort of a spec. They tell us it has to be 1, it has to be 1 minus delta 1, and it has to be all the way to omega s. It has to be 0, and from omega p all the way to pi, it has to be. This is omega p. It has to be take on these values. So now you pick one of these alphas that's your favorite, and translate those specs into a low pass. So I start, let's say, with let's just for convenience we pick alpha equals 0. So this is omega 2 equals pi. I go all the way to this curve here, and pi translates into 0. So this point translates into this point. And omega p comes here. It hits this thing. Omega p here. Yeah, let me call this omega p2, and let me call this omega s2. So omega p2 hits this thing, and I go all the way to the curve, and out comes omega p1, and all the way down, omega p1. So this range here, if you will, gets mapped into this range here. So because here I had the specs of 1 to 1 minus delta 1, I have to have the same thing here. So this thing gets mapped into this thing. And omega s2, the same thing. Here it hits this thing here and results in omega s1. I call them omega s1. And 0 hits pi. So this point gets transformed into this point, and that point gets transformed into this point. So this thing gets transformed into this thing. And here my spec is delta 2. So I just transform my discrete time high-pass filter specs into discrete time low-pass filter specs. And now I am exactly where I was in the last lecture. We already know how to design a discrete time low-pass filter using the transformation technique. What do? We do one more transformation to get into the continuous time low-pass filter, design the continuous time low-pass filter, and then get the discrete time low-pass filter, and then use this to get to the high-pass filter, discrete time high-pass filter. So it's double transformation, if you will. So, yeah.
So what determines the choice for alpha?
Pardon?
What determines the choice for alpha?
What does what?
What determines the choice for alpha?
I'm sorry, what did?
Determines.
Determines. Oh,
Yeah,
okay.
the choice
What
of alpha.
determines the choice for alpha? Alpha is a knob you can choose as you wish. So why is it there? Well, there are times that, for example, suppose you've designed one really good low-pass filter, and you don't really feel like designing another low-pass filter. So, and let's say also you didn't care about, there was no high-pass specs or something. Or this thing didn't matter. So you can pick different values with the same low-pass filter. As I pick different values of alpha, I end up using the same low-pass filter to design different high-pass filters, right? So, I mean, as an example, suppose I have this low-pass filter here, and I'm very happy with it. I don't want to change it. And I want to design 5 high-pass filters. One of them has to have a passband of 3/4 of a pi, another one 2/3 of a pi, another one 5/6 of a pi, another one 7/8 of a pi, right? And that's all I care about. I really don't care about this one. I mean, it's a very artificial example, I'm just telling you. But by picking different values of alpha, I can manage, with the same low-pass filter, I can manage to map this omega p1 to 5 different values of omega p2 and never have to change my low-pass filter. It's a knob. You can choose it any way you like. It's a degree of freedom, if you will. Okay.
So I have a question about the kind of the whole methodology here, and why do we? So I see that this thing has the alpha parameter, and we can kind of play with that and get different results. But why? And it seems to me like the alpha equals 0 is the same as just shifting. So we have, if we just have a low-pass filter, we can just kind of do the multiplication by e to the j pi and just shift it up to pi. And I think that actually is the same case as alpha equals 0. But we could also do something like take something that's just 1 in the whole band, and then subtract away our kind of low-pass filter that we designed before to make kind of like a high-pass filter. So what's the...
Does that meet the specs, though? This is the whole thing we're talking about.
You can make specs. I think you can make specs, and they kind of flip if you did something like that. So you kind of your delta 2 would be kind of the spec on your high-pass filter in the pass band, kind of thing like that. But so
but with this, what you just said, if I have a low-pass filter and subtract 1 from it, the relationship, for alpha equals 0, that's the exact same thing that you're just saying happens. But what if, that alpha equals 0 case is more or less equivalent to that case.
So this is like more general, pretty much.
That's more general.
Okay.
That's right. Okay, so now what would be, if I were to sort of write down the steps one more time, what would it be that, what would be the steps that we have to go through, just to have summed it all up so that you get a big picture of what's happening. So once again, so the steps for high-pass filter, IIR, digital, well, high-pass filter, IIR, discrete time, using approach 2 of bilinear transformation. And I'm going to bring back this thing, page 8, yeah. So it's the reverse of this thing. So first of all, we start with specs for a discrete time high-pass filter. So given the specs for discrete time high-pass filter, that's given from some system design. And now we have to translate that specs into what? Discrete time low pass filter. So translate the specs from discrete time high pass filter into discrete time low pass filter. And we need to use the discrete to discrete transformation, and that's what we talked about. That's today's lecture. Right now I just told you how we do that. That's this transformation and this alpha thing. This whole page is telling you how to do it, right? This mapping that we came up with, etc., etc. And then step 3, now we have specs for discrete time low pass filter. Design the low pass filter. So design the discrete time low pass filter. But that we already talked about in the last lecture, and it already was comprised of 3 steps, A, B, and C. What were the steps? One is translate the specs of the discrete time low pass filter onto a continuous time low pass filter. Step B was design the continuous time low pass filter. Okay, and step C was transform the continuous time low pass filter onto discrete time low pass filter. So that's how we designed this. This is, last lecture, if you will. And then step 4, which is map to step 2, is a dual of step 2. Now that we designed this discrete time low pass filter, transform it back to discrete time high pass filter. So transform the discrete time high pass filter onto a discrete time low pass filter. And the way we do that is what we just talked about. H sub d of z2 is h of z1, with z1 replaced with minus alpha plus z2 over 1 plus alpha z2. Question? Oh, yeah, thank you. Thank you. There's at least one. Okay, thank you. And so, just so that you have a sort of a concrete example of this in mind, are there any questions on these steps? Okay, I think I'm going to just... Yeah, sure. Pardon? Alpha is arbitrary. You can choose it. It's equal to 0 if you want, equal to 1 if you want. Yeah, and as you change alpha, you end up with different specs on this domain. And let's just see. Actually, it's a good question. Let's visually examine how. So, as alpha becomes larger, this curve becomes more like steep, like that. So, in some sense, let's say alpha was equal to 1, then omega p2 would be very, very close to pi. That means this will be very close to this. That means this band, so this distance will get increased, right? And as this one and this one will hit, let's say we hit alpha equals 1, would also be very close to here. So the transition, so for alpha equals 1, it might just be, you see, for alpha equals 0, there's a good healthy distance between these two frequencies, these two guys, omega p1, omega s1. When you go to alpha equals 1, this and this will become very close, so the transition width became smaller in some sense. Right? And it's all the way at this end. Now, if I pick alpha equals minus 1, it would hit, both of them would be very close, and they would be at this end. So alpha equals 0, it's sort of, and again, I'm exaggerating. This is, but alpha equals 0, it sort of gives you a balanced thing of these two giving you a nice transition width in the low pass. I guess I want to emphasize that alpha is a free design parameter. You can choose it as you wish. It's not a, it's a degree of freedom that depending upon what else is going on in your domain, in the problem domain that you're dealing with, that you can choose it to your advantage, if you will. Okay, let me put this back. Any other questions on this?
Question. Do you use the same alpha for step 2 and step 4?
Oh, absolutely. Absolutely. That's a very good point. The most important thing is you pick alpha is arbitrary, but you really have to choose the same thing in both of those. So this, just let me give you a pseudo example of how all of this gets put together, just to clarify things one more time. So you're given a discrete time high pass filter, the magnitude of h of omega. So somebody has told you that between 0 and 0.5 pi, it's got to be have ripple of 0.2, and between 0.8 pi and pi, it has to have a ripple of this much. Then, so that's the specs that's given. That's step 1, if you will. Now we want to translate the specs into a discrete time low pass filter, and let's just pick omega 1 plus omega 2 equals pi, and what that corresponds to is that we have 0.8 gets mapped to 0.2 pi, and 0.5 gets mapped to 0.5 pi, and this is just pi. So here, so this spec here gets mapped into this spec here, and this spec here gets mapped into this spec here. So 1, 0.7, and then 0.2. So that's our specs for discrete time low pass filter. And now you end up designing this low pass filter, and I won't go into the details of it. But if I design that discrete time low pass filter, I get h of z1 equals 0.2416 z1 inverse over 1 minus 1.16 z1 inverse plus 0.414 z1 to the power of minus 2. And that's our low pass filter. And then I just go back and plug in the transformation that we had, which was this thing with alpha equals 0. That transforms into, you're going to have to replace what? z1 is equal to minus z2. That's all there is to it. So transform the low pass filter discrete time into a high pass filter discrete time, and all you're doing, so h of z2 or h sub d of z2 is replace the z1s with minus z2. So you get minus 0.2416 z1 inverse. 1 replace z1 with minus z2, so 1 plus 1.16 z2 inverse. And then here I replace z1 with minus z2, but it's squared, so it just doesn't make any difference. 0.414 z2 to the power of minus 2, and boom, that's our high pass filter that we were after. Because when you let alpha equals 0 in this thing here, when you let alpha equals 0, all you get is z1 is equal to minus z2. Okay. Any questions? In the remaining maybe 1 or 2 minutes that's left, I'm not going to start a new chapter or a new topic now. I would like to get a show of hand, at least of the people who are here, as to how many of you have seen discrete Fourier transform before. Everybody raise your hand. And who has not seen it before? And of those who have not seen it before, how many are undergrads? And of this, raise your hands. Okay. 1, 2, 3, 4. And of these undergrads, have you all taken 120? Have you taken 120? With Gaspar? And he didn't cover DFT. Okay. And are there any other undergrads in this room that took 120 with Gaspar? Besides these that first raised their hand.
Sometimes it's called a discrete time Fourier series. Maybe that's the...
And of the ones who have seen it, how many are undergrads? Okay, raise your hands, please. And of those undergrads, who did you take it with? And you? And you? How many weeks? Let me ask this. For undergrads who took it with Gaspar, how many weeks of DFT did you guys do? That's a better estimate. I mean, I could just mention the word DFT for like 5 seconds and not really cover it. So how many weeks did you guys did? How many? Let me ask this. How many of those Gaspar students think that you did like 2 lectures of it only, or 2 lectures or less? You think you did 2 lectures and less?
I mean, a little bit.
How many think you did 4 lectures or something?
I think at most 4 lectures.
At most 4 lectures.
I think
So I want to know to what extent I should go over it. I mean, there's a possibility that we spend the rest of the semester doing DFTs and teaching you how you can use DFTs to do convolutions and talk about overlap add and overlap save. My goal is extremely difficult, is to figure out what I should cover so that it's a fair... So let me do one more. Raise your hand if you've seen DFTs before. One more time. Okay.
Don't count my mini lecture in session way back when.
Right. Right.
That wasn't
Right. And go ahead.
People like who remembers it, like I've seen it, but it's been 3 years ago.
No, I mean, there's one thing that if you've seen it and you want to remember it, that requires a 1 lecture refresher by me. But honestly, there's 8 lectures left till the semester is over. And do I want to give 1 lecture as a refresher? Do I want to give 8 lectures or spend the rest of the semester talking about DFT? I mean, in my mind, it's one of the most important topics in all of these signals and systems courses. And so, I mean, actually, this course is as much yours as it is mine. I'm here to serve you. I'm here. I can teach you whatever you guys like. And I can spend the rest of the semester just grilling you or dwelling over DFTs and FFTs. Or we can just say, if you all know it, let's move on and talk about something more exciting like speech coding or video or short-term Fourier transforms or wavelets. There's a lot of interesting topics. I actually have been looking forward to getting to this point in the semester where, we can do, there's a little bit of a flexibility to do some more advanced topics, but we can only do that if you really know the basics. Yeah. Were you going to say something?
Well, I mean, if we just take a more advanced course, if we cover those more advanced topics, then it probably makes sense to cover the basics that it appears many of us don't know.
What's the special method used here?
Well, DFT is the only transform you can actually compute. All of these are garbage, Not really good. They're all conceptual.
And there's a difference between the discrete time Fourier series also and the DFT. So you might have seen, it's not major, but there's like aliasing issues in one.
Well, every time you talk about series, you're talking about periodicities, and DFT doesn't assume any periodicities. It's just...
So, the people that think they've seen the DFT, do you guys know that there's aliasing issues involved with that? So, yeah, you should go.
No, I think your comment is scaring them off.
It's not
Well, let me ask you a different question. How many of you know how to use DFT to do convolutions? Okay, and where did you learn it? Like Andy? I guess you did so much speech you couldn't have avoided that topic, right?
Taking a lot of classes up and around.
Right. How about you two guys? Was it an undergrad course or here in Berkeley? Okay, somewhere else. Okay. And how many of you have heard of overlap add or overlap save or things like that? Okay. And how many of you know how FFT works? Again, was this an undergrad class in Berkeley or somewhere else? Somewhere else. Okay. See, I can't really control much about undergrad courses elsewhere because everybody comes from a different school for graduate students, but we do have to tailor to our undergrads who were brought up in our own system, and that, if you say, 120 is a prereq for this course, and if 120 consistently teaches DFT and all these topics, then it's not a good idea for me to repeat it at that level of length. Okay, let's end the class. I'll look at some of the notes and decide how much